Thank you for the nice introduction. Good afternoon, everyone. It's my honor to be here to present our paper. My name is Liang Tong, and I am a PhD student at Washington University in St. Louis. First, I would like to start with the background and motivation. As we know that machine learning has been widely used in security applications, especially for detection. For example, we can use machine learning techniques to detect malware, intrusion, attack or spam or phish. And a general approach is that we start with a connection of training data, which contains entities and their associated labels. And we then carefully design a feature extractor which can extract numerical features from the entities into features. And those feature vectors together with the labels will be used by a machine learning algorithm to get a classifier. And this classifier can be further used to predict previously unseen entities at the test time. Although machine learning has a lot of success in security applications, recent research shows that they're actually vulnerable to evasion attack. Evasion attack happens at the test time. That is, the attacker can manipulate an entity so that the resulting feature vector will be misclassified as benign. We call these attacks realizable attacks because they are realizable in actual entities. For example, the adversary examples produced by realizable attacks can be real-world valid PDF file or the source code of malware. One of the most important aspects of realizable attacks is that those attacks work on entities before being translated into features. Another important aspect about realizable attacks is that after being modified, the attack should be verified with its effectiveness. That is, we use sandbox or other approaches to make sure that the adversary example still preserve the malicious functionality. And sometimes realizable attacks is difficult to implement because we need domain knowledge and a lot of engineering work to implement them. So this can even be very harder and can be individual research project. So since realizable attacks is very difficult to implement, so it's natural to consider whether there are other ways to attack, perhaps in a more abstract way or more simply way. So here is feature space attacks. Instead of working on entities, the feature space attacks work on features. That is, the attackers start with a feature vector of a malicious instance and then directly modify those features. And generally, the feature space attacks can be formulated as optimization problems where the feature values can be arbitrarily modified. Please note that the feature space attacks is not always be realizable because when we solve an optimization problem, sometimes we ignore the interdependency between feature values. So it's very difficult to evaluate the effectiveness of the adversary example, whether they preserve malicious functionality. So to deal with this, feature space attacks, they use LP norm to measure the cost of modification. And oftentimes, the cost of modification is bounded. And as the feature space attack model is abstract and it is much easier to be analyzed compared to the realizable counterpart. Actually, most of the robust machine learning techniques leverage feature space attack model. For example, those approaches using robust optimization, adversarial training, or even the approach using game theory. So this naturally raises a fundamental question, which is at the very heart of our research. Is robust machine learning really robust? Put it in another way, suppose we have a robust machine learning against a feature space attack model. Is it robust against realizable attacks? To answer this question, we made several contributions. Our first contribution is model validation, in which we evaluate the efficacy of defending using feature space attack model against realizable attacks. Our experiments results show that robust machine learning using feature space attack model may fail to provide adequate robustness against the realizable attacks. Our second contribution is model refinement, in which we fix the feature space attack models by using conserved features, which will be detailed later. Our third contribution is generalized robustness, in which we explore the generalizability of defense when we use different kinds of realizable attacks. So now I would like to introduce our methodology and experiments. We use a case study on PDF malware detections. And we choose PDF because PDF files are highly structured. And there have been a lot of existing work on this field for realizable attacks on PDF detectors. And we choose the two most representative PDF detectors. The first one is called content-based detectors, which use content information as the features. For example, the size of a PDF file, or the number of pages, or the number of keywords they use. The other kinds of detectors are called structure-based detectors, in which they use information about the logical structure of PDF. For example, using the existence of some structural passes of PDF. And to evaluate the robustness of a PDF malware detector, we use InvadeML as the realizable attack. We choose this because this one works both for structure and content-based classifier. And InvadeML can produce invasive PDF file, and by using genetic programming. Of course, the adversary examples, they are verified by using sandbox about their malicious functionality. And to validate the feature space attack model, we use a formulation which formulates feature space attack model as a multi-objective optimization. On the one hand, we want to make sure that the modified feature vector of the adversary example can be predicted as benign as possible. On the other hand, we want to minimize the cost function. And to build a robust machine learning, we use a general defense approach, which is called iterative retraining. The basic idea behind the iterative retraining is that we can iteratively use an attack to produce adversary examples, and then adding those adversary examples back into the training data, and then retrain the classifier. So iterative retraining is very general. We can use both realizable attack or feature space attacks to combine it with iterative retraining. And based on the attacks and defense methods mentioned just now, we use them into our model validation. So here is the framework. We use 3 steps to validate the efficacy of feature space models when we use that to defend against realizable attacks. Our first step is that we train an initial classifier or target classifier on clean data. And at the second step, we retrain the target classifier by using InvadeML, our primary realizable attacks. And then we evaluate it with InvadeML as well. So this sounds a little bit self-evident because we use the same attack to retrain a classifier and for evaluation. We use this because we want to have a robust baseline in which shows the upper bound of the defense. So if it is possible to use InvadeML to defend the InvadeML, then the failure of other defense approaches is not due to the difficulty of the problem. So in the third step, we retrain a classifier by using feature space attack models. And we want to see if there is any performance gap between the two retrained classifiers. One is retrained by realizable attacks, and the other is retrained by the feature space attack model. We evaluate those classifiers on both adversarial data and the non-adversarial data. For adversarial data, we use robustness as a metric, which can be obtained by using 1 minus the success rate of InvadeML, our primary realizable attack. And on clean data, we use ROC curve for evaluation. And then we use our model validation framework on the content-based and the structure-based classifiers. So here is a result on content-based classifier. So the left figure shows their performance on adversarial data, which was evaluated by using InvadeML. And the right figure shows that the performance in non-adversarial data. And the figure shows that without any defense, the content-based classifier is very vulnerable to InvadeML, which shows only 2% of evasion robustness. However, when we use either invade ML or feature space attack model to retrain the classifier, we can get almost 100% of effectiveness. Thus, using feature space attack model to get a robust ML, it works. However, on non-adversary data, we can see a non-negligible gap, which means if we use feature space attack model to retrain a classifier, a lot of benign PDFs are classified as malicious. So which means that the false positive rate is increased. And here is a result for structure-based detectors. And just like the content-based detectors, without any defense, the target classifier is very vulnerable, showing only 2% of evasion robustness. And when we use invade ML to defense, and the robustness to invade ML is about 98%. And however, if we retrain or if we defense by using feature space attack models, the evasion robustness decreased from 98% to 70%. And also we observe there is a degradation on clean data. So that means robust machine learning using feature space models is not perfect. Although it can increase the robustness compared to the target classifier, however, we see some degradation, and also the robustness is not very adequate. So here's the question: can we fix the feature space attack models by using some minimum modification? Our answer to this question is yes, and we use conserved features. Conserved features are a subset of features which compromise malicious functionality if they are removed. So there are two types of conserved features. The first type is that if we remove those features, then the malicious codes or payload will be removed as well. Another type of conserved features are those which will break the PDF if they are removed. For example, there are some features in the PDF. If we remove the PDF cannot be opened. If it cannot be opened, the malicious payload will not be executed. So we have two types of conserved features. And we use a systematic way to identify these features by manipulating each object in a PDF file and evaluating the corresponding maliciousness. We successfully identified 4 to 8 conserved features for each of the detectors we use. And after identification of the feature of the conserved features, we use them to modify the feature space attack models. Actually, everything stayed the same. We use iterative retraining. And the only difference is that the value of the conserved features should be invariant or should be preserved in invasive instances. So after using the conserved features to anchor the feature space attack model, here is the experiment result. And first, for the content-based attack model, content-based detectors, and we found that when we use feature space attack model anchored with conserved features, it has comparable performance on adversarial data compared to other baselines. And also, we see a significant improvement on the non-adversarial data. So the conserved features can improve the performance of feature space attack model. And for structure-based detectors, we found that after being anchored with conserved features, the robustness to the realizable attacks of robust ML using feature space attack model can be improved from 70% to 98%. And also, we can see a significant improvement on the non-adversarial data. So therefore, the gap between the realizable attack and the feature space attack can be bridged by using conserved features. So our third contribution is generalized robustness. So far, our evaluation and baseline defense using invade ML as our primary in realizable attacks. So we have obtained two kinds of robust machine learning against this attack. We can either retrain with invade ML, and this classifier is robust to invade ML itself. And also we can retrain a classifier by using conserved features, by using feature space attacks with conserved features. And so those two classifiers are comparable, but which is better? So we should evaluate with other realizable attacks. So we use a bunch of other realizable attacks to explore the generalized robustness. The first we use is Mimicry Plus, which is an improvement of Mimicry attack. And we found that if we defend with invade ML, one of the realizable attacks, it may be vulnerable to other kinds of realizable attack, that is Mimicry Plus. However, if we defend with feature space model, it still remains robustness to Mimicry Plus. We also evaluate with reverse mimicry, which is a realizable attack that requires zero knowledge of target classifier. Thus, it works both for content and structure-based classifiers. And again, we observe consistent results with those using Mimicry Plus. That is, if we retrain a classifier with invaded ML, it may fail to be robust to other realizable attacks. However, if we defend with feature space model anchored with conserved features, it is still robust. And finally, we evaluate the generalized robustness with a custom attack. This attack exploits a features extraction bug of the content-based classifiers. And particularly, we replace some entries of the PDF with their hex representation. And our results shows that this attack can defeat the classifier retrained by invaded ML. And also, for the binaryalized content-based classifier, and we retrain a classifier just using the conserved features. We found that this classifier can be defeated by the custom attack as well. Thus, the conserved features can be defeated, but the combination of feature-based attack model together with conserved features remains still robust. So finally, I would like to summarize my talk shortly. So first one is that robust machine learning methods which use feature-based attack model may fail to be robust to realizable attacks. Secondly, we can fix the feature-based attack model by using conserved features. And third, robust machine learning using feature-based attack model together with conserved features show more general robustness than the methods which use a particular realizable attack. I think that's all about it. Thanks. Any questions?
Thank you. Thank you. Okay, great. We have time for a question or two. Oh, good. Please. Okay. While you're thinking of your questions, I'll ask a question. Liang.
Yeah.
So you have this note. I'm right here. Oh. You have this notion of conserved features, which seems kind of binary. It's you say basically either it affects the malicious functionality or it doesn't.
Yes.
But I could think of detection frameworks where there's a feature that it's not totally binary. Like in the case of spam or phishing or and so forth. Often it's like, well, you got to change your ISP, or you need to come from a different address space, or so there are scenarios where there are features that aren't quite conserved, but maybe they're a little bit more rigid. Like, does your model take into account that a conserved feature might not be just black or white, yes or no, but maybe sort of conserved?
Yes, that's a very good question. So actually, in our case study, we just identify conserved features for the classifier using binary features. Yeah. So it is an open problem whether for the detectors using real value features, because we are not very sure. Yeah. So how to give a correct definition of conserved features for real value features, because the attacker can just do some minimum modification within some range, right? And so this leaves as an open problem in our paper.
Okay, fantastic.
I just have a small question to.
Got some challenges here.
That's fine. That's fine. So just have a question to make sure I understand your methodology.
Sure.
So by conserving a feature, you basically fix it.
Yes, I fix the value of it.
Okay, so after the perturbation, it cannot be changed. That's the constraint.
Yes.
Okay, I see. Thank you.
Yes, so that means the feature value is conserved or preserved because in feature space attack model, actually we are solving an optimization problem, right? So we make hard constraints on this optimization. That is, the value of the conserved features should not be changed.
So basically, you are shrinking the perturbable space.
Yes.
And that's part of the reason that the robustness is kind of increased.
Pardon?
So that's one of the reasons that the robustness is increased, because the perturbation space is smaller.
Yes. The perturbation is smaller doesn't mean that the attack is weaker, because as we mentioned that the feature space attack model, it has a gap between, there is a gap between feature space attack model and realizable attacks. Our intuition is that feature space attack model anchored with conserved features make it more similar to realizable attacks.
Okay.
This is an orthogonal problem with whether the attack model is strong or weak. This is a problem with whether it's similar to realizable attacks.
Okay. Thank you.
All right, let's thank Liang for a great talk. Thanks.
Thank you.